Okay, so let me start. First of all, I want to clarify something. Okay, I hope this is working. I don't know. okay, it's working. So I talked about some ambiguity about. So this is strange. I think I don't know how to. So we had this one. D dt, capital D, d dt. Then we also have partial t. And the difference was not clear. And I asked some friend of mine about who is familiar with this kind of thing. I asked him about this program. Then he told me that this is actually same according to his opinion. I'm not sure. I don't see any official explanation in textbook. But according to him, my friend, this is just emphasis. This is just emphasis that it is total derivative. Okay, and for this one, sorry, okay, for this, just by definition, this is total derivative by definition. And this capital D is just the emphasis of this total derivative. Yeah. And this, the other one, this is partial derivative. Partial derivative. Okay, so if you, that's it. Actually, okay. One example. If you write, if you want to differentiate total or partial differentiation of this function, yeah, xt. Yeah. If x is also a function of t, then the total derivative is like this, right? You have partial derivative with respect to x, then you have total derivative dx dt, plus then you have partial derivative of this with respect to t, right? And partial derivative, you ignore. If partial derivative, you set x constant. So then this is just that means you can ignore this x. X is actually a function of t, but you can just ignore this x part and you take derivative with respect to t. So this is partial derivative. Okay, so then another thing about total derivative. I think I can use this example. Yeah, I can use this example for total derivative. Yeah, so this total derivative actually means like this. So you have a limit. You take a limit delta t goes to 0, right? This is a basic definition of differentiation. Then you have integration along path C, but this C is at time t plus delta t. See, everything is a t plus delta t. Then you have phi, yeah, and x. This is a function of t, but then you have delta t here. Then phi is also a function of t, so you have t delta t here. Then dxi, yeah. So then minus the path is now a path of t. So idea is like all particle, all particle, all particle are same. The collection of particle is fixed. So this is what I want to say. The collection of particle is fixed. So if you have like path C, so you have particle here on this uh, path. You have particle, right? And these particles are fixed. This collection, like if you have 1,000 particle, these particles are fixed. So, but this C, contour C may change, right? So this C change from this one to this. Actually, what I should say, yes, C was originally C0. So you have here you have particle x1, x2, x1000. For example, you have many particles, and you just chase these 1000 particles. Okay, so then this is t equals 0. Then this go to this contour. So for example, this is CT. So then you have 1000 particle makes some kind of line or curve. Then the time change to t plus delta t, then this contour change. For example, like this, some other shape. But then the particle on this contour are same. Okay, these particles on this, we just chase same particles, same 1,000 particles, maybe 10,000, 100,000 particles. We just chase these particles. Okay, so now how you consider the total derivative? Then you have the function here is of x, which is at time t, then t dxi. That's it. This is fine. Let's see. Okay, so then you have dt downstairs. So this is the total derivative definition. d dt phi integration phi dx I. This is definition. So everything is time dependent. See, phi itself is time dependent, as you can see here. Then x is also time dependent, and contour is also time dependent. Right? Everything is time dependent. Then what is fixed is particles, all members of particles. Let's see. Many particles. We actually, in principle, we have to consider infinite number of particles, and these particles are just the same in all equation, and these particles sit on contour C0 at t equals 0. Then these particles sit on contour Ct at time t equal t. Then these particles sit on contour C plus delta t when t is t plus delta t. Okay, so this is fixed. This is fixed. This is fixed. Okay. So let me see. So this is equation. So this definition of total derivative. Yeah. Because everything is a function of t. So then this mysterious sentence. If C is fixed curve, this is like if I would say, what is the most clear way to say? If no particles on C moves. This is the exact meaning. So you have a contour C at time t. This is time t. There's a particle, like an infinite number of particles on this contour. But all particles on this contour doesn't move. Don't move. No particles move. They stay still. They stay at same place, same position. Then you can see Vi here is 0, right? So this completely eliminated. Then this total derivative here become partial derivative. Yeah? Because if particle doesn't move, phi, okay, if particle doesn't move means this. X t plus delta t is just xt. Yeah, the position doesn't change. Position of the particle doesn't change. So you don't have to worry about time dependence of x. So this becomes partial derivative. This guy becomes partial derivative. Yeah, so I think this is clear now. So then we go to the volume integration. Yeah, to consider volume integration, we have to do this. See, this thing, you have intermediate equation. Yeah. So you have anyway, you have volume. It's a little bit strange. Because this total derivative also should apply on contour. But anyway, okay. Let me not go into this point because it's too difficult for me. Okay, so let's just forgive me about ignoring this subtlety, but we just apply this one here. Okay, so we have d phi dt. I'm sorry, dt and dv. Then also we have phi x d dt dv. This is what we have. Too bad I screwed up. I'm sorry, I screwed up. Here. So you can see we have worked out this one. This is what we have to follow again. So here this one I don't derive again. We just accept. dv is j dv. Okay, and ddt, if we take total derivative of dv, because d large v is constant, so we just take derivation on j part, right? J part. Then this one, because j is a function of 9 parameters, so we have this one. Yeah, so then for this, how did we do this? I forgot technique to do this. Let me see. Let me go to another page. I forgot to do this technique. There was some. I think we have to do some complicated thing. This one. Yeah, so this is not so difficult. So this thing, this is not complicated. This thing is just a partial alpha Vj. Yeah. Then partial alpha actually means partial xi, partial large X alpha. Then we have partial Vj, partial xi. If we use a small xi as an intermediate parameter. Yeah. And here actually is we use, so this is I. This is type. This is I. Yeah, so to avoid confusion, we have to use this is I. This has to be J. Yeah. So then we have partial. This thing is first one. Xj is the second one. Yeah, actually, this thing is the first one. Then we have xj derivative. That's this one. Then we have vi. Vi is the last one. Then, observing that the partial derivative of j is a cofactor, so this is another thing. We stop argument here. So this is also a cofactor. This is a cofactor. We accept. I think we have done this for so much. So then we can put this one. I think we can put this thing here. So that means we have j partial I x alpha partial alpha xj partial j vi. This is what we have. dj dt. What I see is dj dt equal this. Then so crazy to do this. This part, I think we can do not this part is like partial x alpha, partial small xi, and partial small xj, partial large x alpha. Yeah, so we can put order this way. We put order this way. So then now we see this is the intermediate parameter. X alpha is intermediate parameter. So this one become delta, Kronecker delta, ij. Yeah. So then we can choose either j or I. Now I choose, so j is a summation. J, we can take summation. So j and j here. So if j hit I, this become 1. So delta j just change this j to I. So finally we have j is here, partial I here, then vi. So we have this one. Finally we have this. Then we go back to this dj dt dv. I got confused. dj dt dv. This one, this is dj dt dv. Okay. So where does this j go? Okay. So then this is like this. Partial I vi j dv. Okay, and this j dv is small dv. So this is partial I vi dv. So now we have this. So now we have this. Yes. So that's why we have this. This part become this. right? Then the strange thing is total derivative is now became partial derivative. I think we did total derivative somewhere, right? Area. Yeah, I think this is the thing. Total derivative is like this. No, no, no. Do I have this one? Yeah. This is total derivative. This is the total derivative. Partial derivative. uh, so we have this is partial derivative here. We are talking about this thing. This is partial derivative times partial A x partial phi x I, for example. Then xi partial xi t partial xi partial t for fixed x. And this is velocity. This is vi. Yeah. So you have this v here. You can rewrite this partial I phi vi plus this partial phi plus phi partial I vi. So this one you can see carefully. This is the derivation of product. So this is more like you partial I phi vi. This thing. This thing here is a partial v. So you will see here. Okay, so I think we successfully derived this part. So then again, for spatial volume, it's not for spatial volume. If the spatial volume, if the volume V is fixed in space, if the volume V is fixed in a space. If the surface S is fixed in space, if the volume V is fixed in space, then as you see above, here you can see above, if the volume is fixed, velocity is zero. So because this means if the volume V is fixed in space, this means all particles don't move. All particles don't move in V, so Vi is zero. Velocity of particle is zero. So we don't have second term, so you have this one. Okay. So next section, we go to deformation rate, spin, and velocity, vorticity. We have introduced the deformation rate tensor D and the spin tensor W as this way. Did we introduce this? This is too complicated, right? Strain rate. I think maybe we stop here for the chapter 6. Then we move on to chapter 7. Yeah, we can come back chapter 6 if necessary, because I think this is too much detail. So we can stop for the moment up to here. Okay, here we stop. Then next video we move on to chapter 7. Okay, so let's stop. I don't know how I can stop this.